Welcome back to the Foundry by Forge College. I'm your host, and today we are rolling out the blueprints for a highly anticipated explainer. We're going to take a deep, technical look into the anatomy of Cloudbreak's data structure. Now, don't panic. We are going to map out exactly how state storage is organized, both on disk and in memory, to give you the foundational understanding you absolutely need without, completely melting your brain. Okay, let's dive into this. Cloudbreak is an incredibly advanced piece of database engineering, and honestly, its abstract components can sometimes feel a bit difficult to pin down. So, to make these advanced concepts instantly accessible, I want you to hold a really specific mental model in your head today. What if Cloudbreak was just a massive, highly engineered library? Keep that image locked in because it's going to make understanding the underlying architecture brilliantly clear. Here is our game plan for today's explainer. We'll start with moving from layout to anatomy, then cover the 4 core components, explore our library mental model, trace a data read, trace a data write, and wrap up with takeaways for partitioning. Let's get right into it. Section 1. From layout to anatomy, bridging metrics to structure. This directly bridges us from our previous lesson on the scalability and distribution implications of Cloudbreak. In that one, you looked at concrete metrics, things like average read amplification and tail latency. But look, knowing a layout causes lag is really only half the battle. You need to know exactly why it happens so you can actually fix it. The simple truth is, physical layout directly shifts measurable operational behavior. The metrics you observe aren't magic, and they certainly aren't out to get you. They are directly caused by the physical structures we're about to examine. Moving on to Section 2, the 4 core components, the anatomy defined. Now, what's really interesting about this slide is the critical distinction between what lives in blazing fast RAM versus what lives on the much slower disk. Cloudbreak's state storage essentially decomposes into 4 interacting parts. First, the logical index, which routes keys and lives mostly in memory. Next, partition metadata, which also lives in memory but has a small on-disk manifest. Third is the in-memory cache. Actually, you might also hear it called the hot table, and this lives entirely in RAM. Finally, we have the on-disk segments persisting your cold state. Understanding exactly where these reside is absolutely crucial because it defines precisely where your performance bottlenecks are hiding. Section 3, the library mental model. Catalog, desk, and shelves. All right, now that we have the technical names down, let's bring those blueprints to life and separate our concerns. Over on the left side, we have logical mapping. Think of this like a library card catalog. It's fast, it's cheap to search, and it happens mostly in memory. On the right side, we have the physical layout, the actual massive storage shelves. Walking to a far-off storage room takes real time, which perfectly corresponds to the heavy lifting of a disk seek in a database. Let's map out this full library analogy so it's crystal clear. In this model, your account keys are the book titles. The partition metadata is the library catalog that maps those titles to specific sections. The in-memory cache is the librarian's desk, where recently used books sit for immediate access. And the on-disk segments, those are the storage room shelves holding the vast majority of the collection. This mental model predicts the effect of changing your storage parameters perfectly. I mean, think about it. If you buy a bigger librarian's desk, meaning you increase your in-memory cache, you can hold a lot more hot books, reducing the need to constantly walk back to the shelves. Section 4, tracing a data read, fetching a book. Let's move to and see how this builds when we put our library into motion. We're going to track exactly what happens when you query an account, or in our analogy, fetch a book. Step 1, you check the card catalog in memory. Step 2, you read that catalog to confirm the exact shelf. Step 3, you check the librarian's desk. Now, if the book is sitting right there, you grab it immediately. Boom, 0 disk I/O. But step 4, if it's not on the desk, well, you have to hike all the way back to the specific storage room shelf and fetch it from the on-disk segment. Finding the book at step 3 obviously saves you a whole lot of heavy lifting. So what does this all mean? Well, this analogy perfectly defines a notoriously complex metric, read amplification. If your shelves are a total mess, meaning multiple scattered segments contain older versions of the exact same key, the system has to work overtime. Just imagine a poor librarian wandering between 5 different dusty storage rooms just to piece together the latest valid version of a single book. That wandering, that is read amplification, and it is exactly why uncompacted segments will severely bottleneck your read performance. Section 5, tracing a data write, returning a book with notes. Okay, so what happens when you return a book with some fresh new notes scribbled in the margins? Step 1 is local write staging. The updated book is basically just dropped on the librarian's desk. That's your in-memory write buffer. Step 2, the catalog gets updated to point to the new version sitting on the desk. Step 3 is the durability flush. Periodically, someone takes all those piled up books and batches them back onto the permanent shelves. Think about tail latency here for a second. If the librarian leaves too many books on their desk without flushing them to the shelves, the desk gets completely buried. New arrivals get pushed into a slow queue, and your latency just spikes. And that brings us to compaction, the unsung hero of our story. Compaction is the background process of reorganizing all those scattered books into nice, efficient stacks. Yes, it consumes I/O energy and CPU power right now, but it reclaims shelf space and saves the librarian so many future trips between rooms. In database terms, successful compaction today drastically reduces your future read amplification. Finally, Section 6. Takeaways for partitioning. Principles for the architect. So, the crucial point is this. Before you go off designing your own partition schemes, you absolutely must remember these 3 principles. First, always separate logical mapping from physical layout. They are 2 very distinct levers. Second, weigh your short-term speed against your long-term operational costs. Sure, giving the librarian a bigger desk speeds things up today, but it completely changes your compaction pressure later down the line. Third, trace pathological behaviors directly back to specific structural components. Understanding these systemic structural behaviors is exactly the kind of deep thinking we emphasize across all the learning programs inside the Forge College curriculum. Which leaves us with a final provocative thought. Now that you know exactly how this massive library works, how will you rearrange the shelves to meet your specific workload goals? Well, that is exactly what we will tackle in our next lesson, Data Partitioning Strategies in Cloudbreak. Until then, I highly encourage you to visit forge.college to explore more educational resources on this subject and to dive even deeper into other advanced Web3 topics. Thanks for joining me on this explainer, and we will see you next time.